Okay, chapter 3 is our first chapter on, or where we actually investigate relationships between two variables. In particular, we're going to be looking at scatterplots and what's called correlation. Correlation is a very common statistical procedure. It's a very simple one of the simplest actually, and it just helps us look at or compare two variables to see if there's some sort of relationship between them. For example, if one variable increases in value, does the other variable also increase in value or decrease in the value in an obvious predictable pattern along with the first variable? Do they change together? In other words, is it possible that one of the variables is driving change in the other variable? That's the kind of thing that we're looking at here with scatterplots and correlation. So in particular, we're looking at what's called bivariate data. Bivariate data, that means that we have two variables that we're assessing against each other, right? And scatter plots are one of the most common ways of doing this, and they're pretty easy to interpret. We'll see some examples of what to look for when you're just looking at a scatter plot itself to see if there's a relationship, or appears to be one anyway, between two variables, all right? And then we'll see a little bit later on in the chapter that if we do seem to have a relationship between two variables as indicated by a scatter plot, we can actually quantify or measure the strength of that relationship using what's called the correlation coefficient, R. All right, and it's very straightforward to calculate. So let's start here. All right, again, we're dealing with bivariate data, right? So that means that for each individual in our study, and the individual can be a person, it could be a fish, it could be a tree, it could be anything that you can measure something about. But for each individual in the study, we have two different measurements that have been recorded, right? So we have two variables, and we're measuring both of those variables for one individual. So each individual has a data point made up of two numbers. All right, so take a look at this data here on the right. What you're looking at, first of all, in the first column is student ID. This is just a way of identifying the individuals in the study. Okay, this is not a variable in our study. Our first variable in this case is number of beers drank, number of beers consumed. So you see this student had 5 beers, this one had 2, this one had 9, wow, and so on. Then we see our second variable is blood alcohol content, BAC. So for student number 1 who drank 5 beers, he or she had a blood alcohol content of 0.1. Student number 2 drank 2 beers, had a BAC of 0.03. Now, by thinking about this, you should realize that there might well be a relationship between the number of beers that a student drinks and their blood alcohol content. You might think that the more beers they drink, the higher their blood alcohol content, and you would be right. But this is the relationship that we're looking for here. Okay, so we look then to see if there's a relationship between these two variables, right? By relationship, we mean, do the changes in one variable result in or tend to be associated with changes in the other variable, right? So here in this example, with number of beers and blood alcohol content for each student, we have two quantitative variables. We can measure them or describe them with numbers. And we talked about quantitative and categorical before. These are both quantitative. So how many beers consumed and their resulting blood alcohol content. All right, so let's look at a scatter plot. So a scatter plot then is just used to display the relationship between two quantitative variables, right? They're very commonly used for bivariate data. Each of our two variables makes up one of our two axes. So you see we have, for example, a number of beers here on the x-axis and then our blood alcohol content here on the y-axis. Now again, student ID here is not a variable, so these numbers are not plotted on our graph. Okay, so we take a look at this, you see that, well, okay, it looks like that as number of beers increases, so does blood alcohol content. We see that we have sort of a relationship here where as one variable increases, so does the other, right? So each of these data points, look at this data point here, for example, that's highlighted. That is 3 beers consumed at 0.07 blood alcohol content, something like that. That is this set of data right here. So we have student number 7 drank 3 beers, resulting BAC of 0.07. 3 beers, 0.07 BAC. So each data point is a combination of these two variables. It's X, Y data, right? It's like coordinates, for example, on a Cartesian plane that you might do, deal with in algebra class, right? Okay, so this again is sort of showing us that we seem to have a relationship. The scatter plot's showing us we have a relationship between number of beers consumed and blood alcohol content. But we don't really know how strong the relationship is. We haven't calculated the correlation coefficient yet that will quantify that strength of that relationship for us. But we can see that we do have an obvious sort of upward slope to our overall spread of data, which I'm circling right there. It seems like there's a relationship. Okay. Now, these two variables, a very important concept here is that of response and explanatory variables. Usually when you have a relationship between two variables, one variable is causing the other variable to respond in a certain way. So we have what's called an explanatory variable. That's the variable that is driving the relationship. And we have a response variable. That's the variable that is being affected by the explanatory variable. Sometimes we call the response variable the dependent variable because it is dependent on the explanatory variable, and therefore we call the explanatory variable the independent variable because it's not dependent on the response variable. So for example, if we look down here at our blood alcohol content scatter plot, again we see number of beers consumed and resulting blood alcohol content. Well, if you think about it, if you drink 3 beers, that's going to cause you to have a specific blood alcohol content, dependent on whether you had a meal recently, your weight, your metabolism, various other things. But the number of beers is causing you to have a blood alcohol content. Ask yourself this: can you have a blood alcohol content if you have not consumed any alcohol? No, you can't. That means that blood alcohol content is dependent on number of beers consumed. So blood alcohol content is our response or dependent variable, and number of beers consumed in this case is the explanatory or independent variable. It's explanatory because it explains your blood alcohol content. It causes it. It's called the independent variable because it is not affected by blood alcohol content. Your blood alcohol content doesn't dictate how many beers you consume. That's backwards, right? That's not how it works. So typically one variable will drive the relationship with the other variable. Whenever we have an obvious explanatory variable, we put that on the x-axis, the horizontal axis. Okay, that's just by convention. So if you're looking at your two variables and one of them is obviously the explanatory or independent variable, it always goes on the x-axis, just by convention. That's just the way it's done. Your dependent or response goes in the y. Now, if you're looking at these two variables and one of them is not obviously the dependent or the independent, then don't worry about it. All right, that's not critical here at this stage with regard to correlation. But by convention, if one of them is dependent or independent, rather, and you can identify it as such, it goes on the x-axis. Okay, let's talk about scaling of scatter plots. So here you see 4 different scatter plots. They're all actually presenting the same data. You see we have pulse rate versus time spent swimming. So we have time to swim 2,000 yards on the x-axis and our pulse rate. So first of all, you can see that this one has the scaling as such, 0 to 50 minutes and 0 to 180 pulse rate, that all the data is scrunched up into this small area here and you can't really make heads or tails of it. Here, they've expanded the y-axis, or actually contracted it from 120 to 180 versus 0 to 180. So that makes this a better spread vertically, but the x-axis is still the same, so it all looks like it's vertical when really it's not. Let's go look at this one. So here we have the x-axis sort of corrected for that. Now it goes from 33.5 to 56.5 minutes as opposed to 0 to 50, or 40 rather. And you can see that spread the x-axis data out nicely, but we've still gone back to 0 to 180 for our y-axis, so it looks like it's in a straight line. You want to have the data points sort of filling up the available white space from one end of the plot to the other, like this. This is the correct scaling for this graph. And now you can see we do have a relatively obvious correlation there. There's a relationship there. It makes sense. The longer it takes you to swim 2,000 yards, the lower your heart rate should be because you're not working as hard. The less time it takes you to swim it, the faster you're swimming, the higher your heart rate should be. Okay, so scaling is very important. Presentation is important. Okay, now after plotting two variables, okay, on a scatter plot, we then need to look at the overall appearance of that scatter of data points. So we look for, specifically we look for the form, direction, and strength. Remember that, form, direction, and strength. So as far as form goes, is the overall pattern spread of our data points linear? Linear just means straight line. Or is it curved in some way? Do we have sort of an odd arrangement where you have clusters of data points here and there with a lot of space between them? Do we have sort of a random shotgun blast pattern of our scatter of data points? No obvious pattern, or it looks very chaotic or random. These are the kinds of things we're looking for as far as form goes. Direction. Do we have a positive slope? Do we have a negative slope? Or do we have no slope, a horizontal line, no direction? That's sort of what we're looking for there in terms of direction. And then finally, strength. How closely the points fit the form. Are they widely scattered along the axis of the scatter data points, or do they appear to be sort of sitting very close to an imaginary line running through the data points? We'll see examples of that here in a moment. Then the last thing we're looking for would be possible outliers, right? Data points that don't seem to fit within the overall spread of the data. Okay, let's look at some examples. So here we have a linear relationship, a straight line relationship. If you drew sort of an imaginary straight line through that, you can imagine that line falling in the middle of these data points, and the data points fall fairly close to that line. But it would be a straight line. There's no obvious curve to this, right? It's a straight line. That's a linear relationship. Here at the bottom left, we have a non-linear. You can see how we would have, if you drew a line through that, your line would be curved like this, okay? That's a non-linear relationship. Clearly, a straight line does not explain that pattern. And then finally, here in the upper right, we have a random sort of shotgun blast scatter. There's no obvious pattern. That doesn't do it, that doesn't do it, that doesn't do it. There's no pattern, there's no relationship between, for example, height and hand length, okay? Back here, on the first one, we have power boats registered times 1,000. So this would be 1,000,000 power boats, 800,000, 600,000, 400,000, versus manatee deaths from powerboat collisions. You can imagine that the more boats you have registered on the water, the more collisions there are going to be. And it's a straight line relationship. Termite activity in a fairy circle, right? Oops, sorry about that. Go back down. Versus grass plants per fairy circle patch. And again, obviously here we have a nonlinear curve relationship, okay? All right. Now, what about direction? So think back to algebra class when you were doing plotting variables on graphs, okay? So here we have our power boats registered again versus manatee strikes or manatee deaths. And you see we have the number of manatee deaths increasing as powerboat registrations increase. So as one variable increases on the x-axis, the other variable increases on the y-axis. That is a positive relationship, a positive association. Both variables increase together in value. Or another way to say it, high values of one variable tend to occur together with high values of the other variable. All right, negative association. So high values of one variable tend to occur together with low values of the other. So here we have change in non-exercise activity. So you see we have calories consumed going up, and here we have fat gain in kilograms. So as non-exercise activity goes up, you see we have fat gain going down. So as one variable increases, the other variable decreases. That is a negative relationship. All right. Okay. Now, strength of the relationship. So how closely tied is the change in the dependent variable to change in the independent variable? How closely tied is change in the response variable to the explanatory variable? So here we have time since onset of a cold in days. Here we have cold symptom severity index, some sort of subjective measure of how intense the symptoms of a cold are. And you can see that we have a negative relationship. It appears to be fairly straight, fairly linear. But if you drew sort of an imaginary line through that, you would see that all 5 of those data points fall very close to that line. That's a strong relationship. Now compare that with this plot over here, looking at serotonin transporter level versus straightforward personality score. You clearly don't have a positive relationship. You may have a negative relationship, but it's fairly weak. If you drew a sort of an imaginary line through that, a line of best fit as we call it, a lot of the data points are way off of that line, right? Here's the line, and they're very far from it. So that would be a much, much weaker relationship. There's a lot of variability in that relationship, whereas over here, there's not so much variability. So this would be a strong relationship, and this would be a weak relationship. Okay, what about outliers? So again, we've talked about outliers in previous chapter. They are data points that seem to be unexpected, unusual. They tend to fall outside the overall pattern of the relationship. So here we have our overall pattern of the relationship sort of running like that. Well, this data point clearly falls outside that. If you draw your sort of imaginary best fit line through this, it's the furthest one from it. Now, what about these data points down here? Technically, those aren't outliers because they're within the overall pattern. They're within the overall form of the data, just at an extreme end of it. So here we're looking at age at first word in months for babies or young kids. And here we have the Giselle Adaptive Score, a measure of intelligence, essentially. So what you see here then is that most kids are having their first word between, say 10 months and, maybe 20 months. There are a few who don't have their first word for quite some time afterward, but there's not a lot of data here because most kids speak their first word here. That's why we have these sort of gaps here. But this data point and this data point are still within the overall pattern of the data, so we can't really call those outliers. This one sits way off the axis of the spread of data points, and therefore that's considered an outlier. All right, let's describe these different scatter points. So top left, we're looking at the logarithm of gross domestic product per capita. And here we're looking at the log of child mortality under 5. So first of all, we have a fairly strong relationship. It's negative because as countries or as GDP increases, we have lower child mortality rates. This means that richer countries have lower child mortality rates and vice versa. It's a reasonably strong negative linear relationship between these two variables, right? We do seem to have one outlier right there, okay? But it's just one of a fairly large data set, so it's really nothing to worry too much about. The pattern is very clearly linear with or without the outlier. Now, top right, we've already looked at this data set. This is power points registered versus number of manatee deaths. This is a very strong positive relationship As PowerPoint registrations go up, so do manatee deaths. So this is a positive relationship. It's very strong. You can see the data points fit very close to that imaginary line of best fit. And there's no obvious outlier here. All right, bottom. We've looked at the age at first word versus Giselle adaptive score already. Again, this is going to be at what we call maybe a mild negative linear relationship between these two. The relationship is not so obvious here. We do have, this data point. We do have these apparent gaps in our data here. But overall, there seems to be a relationship between age at first word and a measure of intelligence. Wouldn't be an unexpected relationship either. All right, we can also add categorical variables to our scatter plots. So up to this point, we just talked about quantitative variables. We can add categorical variables as well. Very often, two or more relationships can be compared on a single scatter plot by using different symbols for different groups of points on the graph. In other words, we can sort of subdivide our data points into smaller groups. All right, so for example, here we have a measure of thorax length. You can see that right there in millimeters versus longevity in days. So this is for, I believe, for crickets. Fruit flies. So here you can see that what they're doing is measuring the thorax length of male fruit flies and comparing that to how many days that they've lived. So overall, if you look at the entire spread of data, you can see there seems to be a fairly weak positive relationship between thorax length and longevity. So it sort of suggests that larger flies live a little bit longer. But if we break it down further, we can see an interesting pattern here, okay? You see we have green triangles for one set of males and purple circles for another set of males. So the graph compares the association between thorax length and longevity of male fruit flies that are allowed to reproduce, green, and those not allowed to reproduce, purple. So what you see is that those in green are found here and those in purple here. In other words, these guys were allowed to reproduce, these guys weren't. So for a given thorax length, say 0.75 millimeters, fruit flies that reproduced tended to live less long than fruit flies that did not reproduce. Fruit flies that did not reproduce lived longer for a given thorax length than fruit flies that did reproduce. And that's true at all different thorax lengths. So we have two different groupings here, two different categorical variables, those that were allowed to reproduce and those that were not, and we can see there's a relationship there. Something about reproduction is metabolically, energetically expensive, and we see this a lot actually in invertebrates in particular. Those that reproduce more tend to not live as long as those that don't. There's a cost in terms of longevity to reproductive activity. Okay, so we can glean more information from scatter plots by plotting categorical variables in this way. Another example, energy expended as a function of running speed for various treadmill inclines. Describe the relationship here. Well, if we ignore the incline, right, we have our key right there. If you ignore the incline, all of this just looks like a mess, right? But look at incline. So purple circle, minus 10-degree incline. There we have a strong positive relationship in terms of speed, how hard somebody's working, and how much energy they're burning through. Calories per kilogram of body weight. Here you see a minus 5-degree incline. Here we have a level or 0-degree incline. Here we have positive slope inclines, so going uphill. Level going downhill. And so you can see that clearly in each case, for each of those different inclines, there's a positive, strong linear relationship. You see this one here, you see that one, this one, this one, this one, and this one. But also, look at the slopes of these lines. You see how the slope gets higher and higher as the incline gets higher and higher. And what that means is that Individual is burning more energy at a given speed on higher inclines than on lower inclines at the same speed. And that makes sense, right? The higher the slope you're walking up on the hill, the more you're going to work to do it. So there's a lot more information that we can glean from these things than what you might see at very first glance. And you have to get used to doing that. You have to look at the graph and glean all the information from it that's embedded in it. And there might be more than what you see just on first appearance alone. Okay, now we're going to talk about the correlation coefficient, R, as we call it. This is a statistic that helps us to understand, quantify, and measure the relationship between two variables. Rather than just saying it's strong or weak, now we can put a number on it. So the correlation coefficient is a measure of not only strength, but also the direction of the relationship. We calculate it using the average, or the mean, and the standard deviation of both the x and y variables. Okay, so here we have our data for pulse rate versus time spent swimming. So again, we see a fairly strong negative relationship. It's linear, okay? We're going to quantify that. This is our relationship for doing so. Now remember, statistical notation, as you see here, often looks somewhat confusing and very complicated, but it's really not. We saw an example of that when we calculated standard deviation in the previous chapter. All we're going to do here is calculate some information for our x data and the same information for our y data. So x data is time to swim, certain number of yards. Y data is the resulting pulse rate in beats per minute. So this is our x data, that's our y data. Okay, once we calculate these two numbers for each data set, for each pair of variables, we multiply them together, add them up, and then divide by our sample size minus 1. All right, so first of all, what is x sub I? X sub I is an individual x value. X bar is the average of all the x values. S sub x is the standard deviation of all x values. Same thing for y, our y data set, or our dependent or response variable. Y sub I is an individual value for y. Y bar is the average of all y values, and S sub y is the standard deviation of all y values. Okay, so down here we have a mean, time to swim, we have a mean of 35, standard deviation of 0.7. Pulse rate, mean of 140, standard deviation of 9.5. Let's take a look at an example. Here we have a different data set, so I just put 4 numbers in here to make it simpler. Okay, so here we have length versus volume. I believe this is actually data from cave fish that I used to work with. But you might expect that in animals or plants or whatever, there might be a relationship between the length of the organism and its internal volume. Okay, so here we have length of 3, 1, 6, and 4 millimeters, and volume of 8, 5, 14, and 12 cubic millimeters. Our mean here is 3.5, mean of 9.75. Standard deviation of 2.08, standard deviation here of 4.03. When you plug this into Minitab and tell it to calculate the correlation, or you do it by hand using the formula, this is the value of R that you get. Now, R ranges from values between -1 to +1. A 0 correlation coefficient means there's no relationship, okay? No relationship between your x and y. The closer the value gets to +1 or -1, the stronger the relationship, and the sign, plus and minus, tells you the direction, positive or negative. Okay, so we're going to take this data and actually calculate correlation coefficient. All right, so let's look at the next one. I've got a spreadsheet page here where I did the calculation. I'm going to kind of walk you through this. All right, so first of all, we have our x data here in this gray column and our y data there. So this is length, this is volume. For x, for length, we have a mean of 3.5, standard deviation 2.08. For volume, our y data, 9.75 for mean and 4.03 for standard deviation. All right, so first thing we have to do is figure out this value for x sub I minus the mean. So x sub I is each individual value of x. So x sub I minus of 3 minus the mean of 3.5 gives you minus 0.5. So we've just now done this part right here for our first x value. We do it again for our second x value. Next one is 1. 1 minus 3.5 gives you minus 2.5. The next one, 6 minus 3.5, 2.5. The next one, 4 minus 3.5, 0.5. All right, we do the same thing for y. So first value of y is 8 minus 9.75 minus 1.75. Second one, 5 minus 9.75 minus 4.75, and so on down the line. So now we have done the numerator for x and the numerator for y. Next thing is to divide each of those numbers by the respective standard deviations. Right here for x. So we take our x sub I minus the mean for our first data point of minus 0.5 and divide that by 2.08 and get minus 0.24. Take the next one, x sub I minus the mean of minus 2.5 divided by 2.08 minus 1.2, and so on down the line. Do the same thing over here for y. First one, we had y sub I minus the mean of minus 1.75 divided by 4.03 minus 0.43, and we do that for all the other ones as well. So now, with this column of data and this column, we have calculated this value and this value. Now what do we have to do to them? We multiply. So let's take these two columns and put them down here, okay? Multiply x sub I minus the mean over the standard deviation of x times the corresponding y sub I minus the mean over the standard deviation of y for the y variable. That's our x variable, that's our y. 3 and 8. These are the resulting calculations. Multiply those two together, 0.10. So for our first data point, 3, 8, we have now done this entire calculation, and that's the answer for it. Do the same thing for the second pair of data, 1 and 5. Here we calculate the two together, 1.42. We've done that calculation for our second pair of data points. We do it for our third and our fourth. All right, now we have done all of this for all of our data pairs. Next thing we have to do is add them all up. This is the sum. You sum the result of this calculation. So we're going to add up all these numbers. Here's our sum, 2.92. Last thing we have to do is multiply that sum by 1 over n minus 1. When you multiply something like this by 1 over n minus 1, you're just really dividing this by n minus 1. So take your sum of 2.92 and divide it by n minus 1. n is 4, n minus 1 is 3. So 2.92 divided by 3, 0.97. That's our correlation coefficient. It seems complicated, but when you start to understand statistical notation here, you realize you're just doing it step by step, right? It's a step-by-step process, and that's exactly what I just took you through here on this figure. Okay, you should be able to do that. You should be able to do this by hand, so you should work through some examples of that. Make up some numbers, calculate the correlation coefficient by hand, run it through Minitab, and then, or you can even do it through Excel if you wanted to, and then check your work that way. All right, now here's a couple of things about correlation coefficient. It does not distinguish between explanatory and response variables. I said earlier that if you compare your two variables and one of them is obviously the explanatory and one obviously the response, the explanatory goes on the x-axis. Again, that's by convention. That'll become very important when we get to something called linear regression later. But for now, it's not that really all that critical. The reason for that is that with correlation, the calculation doesn't care which of the two you consider to be the explanatory or the response. Here we could do, pulse rate in beats per minute as the x-axis and time to swim 2,000 yards on the y, and you get an r minus 0.75. Flip it around the way it should be, time to swim 2,000 yards, which explains pulse rate, and you get the same correlation coefficient. Time to swim is the explanatory variable here, and it would belong on the x-axis, but you could plot it the other way, and the calculation would still come out exactly the same. So that's what I mean by R not distinguishing between the two types of variables. Second thing about R, correlation coefficient, is that it has no unit. When you take the standard deviation of something, that eliminates all units. Okay, it eliminates units. So by calculating standard deviation, which we've done here in the denominator of this calculation or this formula, you are doing what's called a standardization. Standardization eliminates or gets rid of all units. So you can't say, for example, that this value of R minus 0.75 is minus 0.75 minutes. It isn't. It's a unitless value. So don't refer to correlation coefficient in terms of units. It has no units. All right, and as I said before, the value of R ranges from -1 to +1. And the value of it tells us the strength and the direction. Strength is measured by the absolute value of R, and then direction is indicated by the sign. So here you see what appears to be a random scatter shot. No obvious pattern there. That might be a correlation of 0 if you actually ran the numbers. Here you have a correlation of -0.3. You can see it's a little bit longer this way than it would be that way. So we probably have a negative relationship, but it's very weak. So 0.3, very weak. It's close to 0, and you see it's negative. Here we have, for this one, we have 0.5. So you can see we have a fairly obvious positive relationship, and it is positive. You see it's a positive sign there, but it's fairly weak, 0.5. Here, we have a stronger relationship. It's more narrow than the previous example, but it's clearly negative. Here we have a very strong relationship. It's positive, 0.9. Here we have almost a perfect relationship, almost 1.0, but it's negative. So again, this one value tells you two things. It tells you the strength of the relationship and the direction of the relationship. And again, you see that this one up here is no obvious pattern. This one, there might be pattern here. All right. The thing about R, the last thing here, is that it's not resistant to outliers. Outliers dramatically affect the value, or can dramatically affect the value of R. Correlations, again, are calculated using means and standard deviations, and because of that, they're not resistant to outliers. Outliers affect the mean, don't they? We saw that back in, I think, the first or second chapter. If you're using the median here, correlation wouldn't be affected by that, but we don't use the median in the calculation for R. So, as an example, here we have a nice, strong negative relationship, as you can see. Take one of these values and move it down as an outlier to here, for example, and now you see what that's done to the value of R. So R is strongly affected, not at all resistant to outliers. That's an important thing to remember. Okay, we got through all of this chapter in one lecture video. So this is chapter 3, and the next chapter on regression, we're going to take correlation one step further.